Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about static forces in manipulators. So in the last class we discussed how the linear and angular velocities are propagated from one link to next link. In this lecture we will see an example of velocity propagation for both linear and angular velocities, and then we will try to come with the Jacobian concept which we have seen in the previous class. Okay? And then we will move on to see how these static forces comes in manipulators, okay, and how Jacobian come into picture in case of static forces in manipulators. So by end of this lecture, I expect you will be able to understand how the velocity propagates, similarly how the force and moment propagates, evaluation of Jacobian, how can we do that, and what role is played by this Jacobian. Initially, I will introduce the topic, then we will be seeing the velocity propagation example as I told, then the Jacobian example, singularities example, then static forces in manipulators, Jacobian in the force domain, and finally we will be seeing how can we do the Cartesian transformation of velocities and static forces. So let us take this velocity propagation example. So it is a two-link planar manipulator. So this is your link number 1 and this is your link number 2. These links have got length say L1 and L2 like this. Okay. So as done with any problem, we first fix a inertial frame x0 cap or y0 cap, that is the frame number 0. Then as per the convention given in the Craig textbook, we assume the 0 and 1 frame to be at the same location, same position. So 1 over here, and as per DS notation the link length is assumed to be along x axis. So this is your x1 cap here, right? And at the beginning of the second link we have this x2 cap, alright, y2 cap this one, and yeah, these are the joint angles. Angle between x0 cap and x1 cap is the first joint angle theta 1, and angle between this is the direction for x1 cap. So between x1 cap and x2 cap we have the theta 2. Okay. So I am not going to derive the ds parameter over here. We have already seen in the ds lecture on the ds parameter. So I can get the ds parameter. Then we have also seen this transformation matrix, a general transformation matrix for transformation from ith frame to I minus 1th frame. Okay. So if I put the ds parameter over here in this table, for this case these are the transformation matrix which I get. Transformation matrix for 1 to 0th frame will be basically this 3 by 3 matrix, and it has this component. So this is basically the what R1 with respect to 0. Similarly, this part is R2 with respect to 1, and this part is R3 with respect to 2. Now you see, since frame 3 and frame 2 they are on the same link, so their orientation are going to be the same. So I have the identity matrix over here, and frame 1 and frame 0 they are coinciding. So this vector position vector here all are 0 0 0, and this position vector in the x1 direction basically represents the first link length, and here this represents the second link length. So this way I can write these transformation matrices. Okay, it is a simple problem all right. So, if you are interested, we can do it trigonometrically as well, all right. Yeah, maybe in the later slide I will explain how we can do that. So, here let us, here the angular velocity of the first link expressed in terms of frame 1, that is going to be theta 1 dot in the z direction. As I said, frame 1 origin coincide with frame 0 origin, right. So, it does not have any velocity. So, you have the 0 0 everywhere. This is our velocity propagation equation which we have seen previously. Okay. That is angular velocity of I plus 1th link expressed in terms of I plus 1th frame. Okay. Of course, with respect to some universal frame. This is equal to the previous link angular velocity expressed in terms of same I plus 1th frame plus that joint velocity, that is I plus 1th joint velocity. So, this equation we have seen already. Now, in this equation, if I put I is equal to 1, I come up with this relationship, that is omega 2 expressed in terms of frame 2, and this you have the previous link velocity. So, if I put I is equal to 1 in this equation, this is what I am going to get, right. And in this equation, we have already evaluated this omega 1 expressed in terms of frame 1. So, this is this value. R1 with respect to frame 2, this is going to be same as transpose of R2 with respect to 1. Okay. So, this one we have already evaluated, this one we have already evaluated, this is R2 with respect to frame 1. Okay. So, that one I can substitute it over here. So, we have these values, and this is rotation is about z axis. So, I am putting it over here, and when I do this multiplication, this is what I get. Okay. So, angular velocity of the second frame expressed in terms of the second frame, that is 1 by theta 1 dot plus theta 2 dot here, right, the z component. So, this is how this angular velocity propagate over here. Fine. Next, let us look at how does the translational velocity propagates. So, this is the relationship which we have seen previously. Okay. Here this has to be I plus 1. Okay. So, velocity of translational velocity of the origin of I plus 1th frame expressed in terms of I plus 1th frame will be translational velocity of the ith frame expressed in terms of ith frame plus a omega cross r component over here. Okay. And this everything has to be expressed in terms of I plus 1th frame. So, we need to have this transformation I to I plus 1. Here everything is expressed in terms of ith frame. Okay. So, I can put them in a bracket and do this transformation I to I plus 1, right. So, this way, this is my general velocity propagation equation, right. Now, if I put I is equal to 1 over here, I will be getting this equation, right. V11 we have already seen a 0 vector. Okay. So, this term is not going to contribute anything over here. This one omega 1 cross, I can write it as a skew symmetric matrix. Okay. So, this is written here as a skew symmetric matrix, and this P21 this is basically the position vector of frame 2 with respect to frame 1. So, this is this one only, right, and this expression, all right. So, that we have seen how we have done that. This thing can be done another way. In fact, I can do the this vector cross product. I can take, rather, if I do not want to write in the form of skew symmetric matrix, I can just take a vector cross product. Okay, and I will be getting the same result, all right. So, that way I can do. Basically, you see what is omega 1, it is basically theta 1 dot, and that is say in the k direction, it is about z axis, and cross this one is about this length we are taking as per ds notation along the x axis. Okay. So, this will be basically L1 say I cap. Okay. So, this is theta 1 dot L1 and k cross I is actually going to be j. Okay. So, this theta 1 dot L1, so this is your here j component. So, this will be the in this column it will be the in the second row. So, either I do it this way, but if you are using any program you are not doing it manually. If you are using say MATLAB or Python any software, then naturally you have to write it in the skew symmetric matrix format and then we can evaluate this one. Okay. So, this is how V22 will be getting this value. Then omega 3 and omega 2 both are going to be the same because as I said frame 3 and frame 2 both are attached to the same rigid link. Okay. That is to the second link. Alright. And we can evaluate V33. Okay. And this V33 of course if in the previous equation if I put here I is equal to 2 in this equation I get this V3, right. So, this one I can get it. Now, this R23 this is a unit matrix because both frame 2 and frame 3 are there on the same link. Okay. So, V2 this we have already evaluated in the previous slide. Again I can write this as a skew symmetric matrix over here and what this skew symmetric matrix is this we have already discussed in our basic concept mathematical concept during this course. Okay. So, that I can write it like that and then P32 I can write it over here. We do this matrix multiplication and summation then I get this V3 value. Okay. So, this is how it turns out to be. Okay. Then if I have to find out say rotation matrix for expressing the orientation of frame 3 with respect to say frame 0, I can do this multiplication of the rotation matrix 3 to 2, 2 to 1 and 1 to 0 and this one will be simply of this form where this C12 means actually cos theta 1 plus theta 2. We can visualize this also because since this is a very simple planar problem, this angle is theta 1 and this angle is theta 2. So, naturally from here this orientation is going to be theta 1 plus theta 2, right. So, the orientation of frame 3 with the frame 0 is going to be theta 1 plus theta 2, right, and that is what this relationship tells you. The one value here indicates the orientation or the rotation is about z axis, okay, and these are the terms associated with the rotation matrix, right. So, then here what we have found out V33, if I have to express this velocity in terms of say frame 0, okay, this frame, then how can I do that? So, this I can do if I multiply this by R30, okay, and R30 is the this one which we have just evaluated. So, I can put it over here V33 we have found out this one, okay, I can do this matrix and this vector multiplication and I will be getting this V30. So, the V3 velocity of frame 3 expressed in terms of frame 3 which we have evaluated, that was this one. So, if I write it as a multiplication of a matrix and a vector, then I can segregate this theta 1 component here and similarly theta 2 here. Then I can write this in this fashion. There is no contribution of theta 2 term over here. So, this term is going to be 0 and this will be L1 S2 theta 1 dot. So, we get the first term. Similarly, if I multiply this, I will get the second term. So, this multiplication or this matrix is what we call as Jacobian, right. So, I can write, and this Jacobian, since I am expressing this velocity of frame 3 origin with respect to frame 3, I call this Jacobian expressed in terms of frame 3, right. So this is how this can be written. Similarly, if I look at say V3 expressed in terms of 0th frame, then this is the expression, right? I segregate this, I write it in terms of a matrix, a 2 by 2 matrix and a vector, that is 2 cross 1 vector. Then this term is what is called as Jacobian, right? And here this is expressed in terms of 0th frame. We have seen the problem of singularity, right? And what the singularity is, as we have seen in the previous lecture, okay, at singular configuration, this manipulator loses one or more degree of freedom as viewed from the Cartesian space. Okay. So, what does this mean? This means essentially that the manipulator may not be able to move in certain direction. Okay. Whatever joint rate you have, but manipulator will not be able to move in certain direction. So, this concept we have seen in the previous lecture. Now, I can explain that mathematically with an example to you. Okay. So, I said we have say velocity vector and this is going to be Jacobian. This is Cartesian velocity vector Jacobian into joint velocity vector. So, if you have to find out joint angles, you have to take inverse of Jacobian and multiply this with the Cartesian velocity vector. So, the question was that what if I am not able to find out this J inverse? So, to find out the singular point in a manipulator, we must examine the determinant of Jacobian, because in the inverse we have the determinant terms coming in that evaluation. Now, where the determinant is equal to 0, the Jacobian has lost a full rank and is singular. So, let us take the same example, okay, the 2 degree of freedom manipulator example, which we have seen previously for the evaluation of the Jacobian, this one. Okay. So, the Jacobian expressed in terms of frame 3, the determinant of Jacobian, okay, expressed in terms of frame 3 will be actually this one. Okay. I am not discussing here how the determinant is found. You can refer to some of the mathematics textbooks. It's very simple for a 2 by 2 matrix how the determinant is found, but for this case this is going to be the Jacobian, right. Now, if I take the determinant of this one, this is going to be L1, L2, S2, and if this is equal to 0, naturally your L1 and L2, these are the link lengths, so they cannot be equal to 0, right. So, it is S2 which has to be equal to 0, and S2 will be 0 if your theta 2 is 0 or it is 180 degree, right. So, you are going to have the singularity, right. What does mean by theta 2 is equal to 0? Theta 2 is equal to 0 means this one, because you are going to have this as x2 cap, y2 cap, and you have the x1 cap here and y1 cap here. So, the angle between this x2 and x1 is 0, right, and this is a singular configuration, because as I said, when you are giving theta 1 a value, this cannot move in this direction, okay, this can move only in this direction. So, ability to move in this direction has been lost at this configuration. Similarly, when your theta 2 is 180 degree, this is what happens here, okay. So, this is your x1 direction, x1 cap direction, and you have the x2 cap direction here, and this is the angle. And in this case also, you see that this manipulator cannot move, end effector cannot move in this direction, okay. So, it has ability to move only in this direction. So, the ability to move in this direction has been lost, alright. So, this is what is meant by the singular configuration, okay. So, let us take example here. Suppose you have this 2 degree of freedom manipulator, say this is your theta 1 and this is minus theta 2. You have x3 cap, y3 cap as the frame attached at the tip of the robot, okay. And suppose this end effector has got a velocity in this x direction of the inertial frame or the origin frame, right. So, the question is that what are going to be the joint angle? So say it is moving by a velocity of say 1 meter per second. Okay. So what are going to be the singular configuration? So in this case, if you look at Jacobian expressed in terms of 0th frame, for this case we have already seen this value, right. So the inverse of Jacobian we can find out. So this is what it is going to be, right. So I can get this joint angle rates as inverse of Jacobian into the Cartesian velocity rates here written in the form of the vector, right. So this is J inverse and this is this value 1 meter, I can put it over here, and in the y direction this velocity is 0, right. So if I multiply this, so from this I get the value of this equation, I get the value of theta 1 dot and theta 2 dot, right. From these values also I see that what happens if your theta 2 becomes 0, okay, then this theta 1 dot is going to be infinite, okay. So both joint rates go to the infinite, okay, at the singular configuration, okay. Next let us move on to the static forces in manipulator. Here we would like to see how the force propagates from one link to the next link in the static condition, alright. So suppose this is your ith link, okay, and you have I plus 1th link over here. Say this Fi is the force which has been applied by the previous link on the ith link. Similarly, this Ni is the moment applied by the previous link, ith link, and ith link applies a force Fi plus 1 on the next link. Similarly, Ni plus 1 is the moment applied by this ith link on the next link, alright. So to do the analysis, okay, what we do is that we first lock all the joints so that the manipulator becomes a structure, okay. Then we consider each link in this structure and write the force and moment balance relationship in terms of the link frames, okay. And finally, we are interested in calculating what static torque must be acting at the joint axis, okay, for the manipulator to be in a static equilibrium condition, okay. So this is the sole aim, alright. Okay, we are not considering the weight of the links here, alright. So as I explained, say Fi is the force exerted on link I by the previous link and Ni is the torque exerted by on the link I by the previous link. So I can take a force balance of the ith link. So this is force applied from the previous link and this is the force applied by the current link on the next link. So okay, so one value is positive, another value is negative, right, and all these are expressed in terms of the same frame, alright. So this is the force balance equation. Similarly, I can find out the torque balance, okay. So if I sum the torque about say this frame, ith frame over here, then what we are going to have this Nii, okay, the torque applied by the previous link, and minus of this value which is applied by current on the next link, alright. And this Fi is not going to contribute anything because we are evaluating it about this point and this force is passing from that. So its contribution is going to be 0, but we will be having contribution from this one, okay, Fi plus 1, and this is acting over a vector Pi plus 1 I. So we are going to have this one Pi plus 1 expressed with respect to I cross Fi plus 1 expressed in terms of I. So this completes our moment balance, okay. So this equation can be written in this form, alright, it can be written in this form, and so this is the force balance and this is the moment balance, okay. And we can write these equation in terms of their own frames, okay. So this Fii, of course this is written in terms of ith frame only. This one if I want to write in terms of the I plus 1th frame, then I have to carry out a transformation here, multiply with a transformation from I plus 1 to I here, and this is from expressed in terms of the I plus 1th frame. Likewise, this one I can do, okay. So this is Ni plus 1, I express it in terms of its own frame. So this is that, okay, and so I need to have a transformation over here, additional transformation rotation matrix from I plus 1 to ith frame, right. And this Fi plus 1 with respect to I, this is same as Fii, so I write it this one and then this will be as it is. So, this way I can write the force and moment balance, and in fact I can use these equation in order to evaluate how this force and moments propagates from one link to another link. So, from this one, if I extract its z component, okay, so that will be, I will be getting basically the joint torque. Okay. So, to extract the z component, okay, I can take the transpose of this one, okay, and multiply with this vector, I will be getting the z component. Alright, for a revolute joint, and if my joint is prismatic, I can get the force over here. Alright. We generally define the positive direction of joint torque as the direction which would tend to move the joint in the direction of increasing joint angle. Okay. So, that way in fact we can evaluate how much joint torque I will be needing. Let us take an example. Okay. So, here in this lecture I am dealing with many examples. You can try practicing these examples and try to understand the concept and have a very clear picture of that. Okay. Suppose in this 2 degree of freedom planar manipulator, there is a force acting, say F, expressed in terms of frame 3, okay, and that force value is, say, this one, and my interest is to find out what joint torques I have to apply so that my robot is able to resist this force which is acting at the tip of the manipulator. Okay, so I can again use this force and moment propagation equation. Okay, so this F33 is given to me. F22 I can evaluate, F33 into R322, this frame 2 and 3, they are on the same link. So, we have the unit matrix I here. So, this is okay. So, this F22 is going to be equal to F33. So, then I can evaluate by putting I is equal to 2 over here, I get N22. Okay. This, if I am putting here 2, then I have N33 terms coming, but I assume that at the tip here this is N33, this is 0. There is no torque or moment acting at the frame number 3 over here. So, this term will be 0. So, I will have contribution only from this one. Okay. And this one I can write as a skew symmetric matrix over here, and yeah, I get this value. Similarly, I can get F11, alright, and this F11 I can get from this equation. Okay. So, it will be in terms of F22 R221. This matrix R21 we already know for this planar case, F22 is this one. So, I multiply this and I get this value. So, next I can evaluate N11. This N22 we have evaluated in the previous slide, F11 we have evaluated just now. Okay. So, I can substitute these values and I can get this N11 value. After this simplification, I can get this value over here. Okay. So, what I have to do from this N11, I have to extract the z component of that. So, it is this value. Okay. So, this much torque you require for the first joint, and previously we have already seen for the second joint I can extract this value, the z component of it. So, this value we require for the second joint. So, this is, I have written it summarized. For the second joint this much torque, and for the first joint we require this much torque, okay, in order to have a manipulator in the static equilibrium condition. Okay. Now, I can write this in a matrix form. So, we have forces here and the torque, joint torque here. So, this is the matrix. Okay. And you can see that this is expressed in terms of frame 3. Okay. So, we get this one. Okay, this matrix as the Jacobian transpose, right. So, this part is actually the Jacobian transpose. So, from here I get this as the Jacobian. The previous Jacobian which we have evaluated, you can compare from there and you will see that this part is the transpose of the Jacobian. Okay. So, this torque is essentially Jacobian transpose into the force acting at the end effector. I can get this expression using concept of the virtual work also. Okay. So, when the forces act in a mechanism, work is done if the mechanism moves through a displacement, and work is a force acting through a distance and is a scalar, as all of us know. It has got unit of energy. So, we can use the concept of principal virtual work, okay, where we go for the infinitesimal displacement, okay, of the force or moments. All right. So, the same amount of energy is required no matter what frame you are considering that. Okay. So, the work done in Cartesian term is going to be work done in the joint space. Okay. So, this is F dot product of say virtual displacement. Okay. And this is the torque into torque and dot product of the virtual you have the joint rotation. Okay. So, if I want to write in a form of say matrix multiplication or vector multiplication, I can write the transpose of this one into this vector, and similarly the transpose of this one and this vector. You see, F is the Cartesian force moment vector, which is 6 cross 1. So, we could have the 3 forces acting at the tip and the 3 moments acting at the tip. Similarly, D psi is the Cartesian displacement vector, where we can have the 3 displacement x, y, z and 3 rotations theta, phi, psi, and tau is the joint force vector. Suppose your manipulator, if it has got 6 degrees of freedom, so you could be having the 6 cross 1. Similarly, you are going to have the joint position vector, that is going to be the 6 cross 1. Okay. So, Jacobian definition we have already seen this one. So, if I substitute this definition in this one, this is the relationship which I get. And if I take the transpose of, now this is going to be valid for any delta capital theta here. So, if I take the transpose of both the sides, this is what I get. And in fact, this is the equation which I written previously over here through this example, right. Okay. The last part of today's lecture is let us see how do we carry out the Cartesian transformation of velocities and static forces. Okay. So, suppose we have the 6 cross 1 representation of general velocity of the body. So, we could have the 3 linear velocities, translational velocities and the 3 angular velocities, right. So, and 6 cross 1 representation of the general force vector. So, we could have the 3 forces, that is 3 cross 1 forces in the xyz direction and the 3 moments, that is 3 cross 1 moments about x, y and z axis. Okay. So, for the velocity transformation, okay, I can use the velocity propagation equation, the angular velocity and the translational velocity propagation equation. Here I have written it for the I plus 1th frame expressed in terms of I plus 1th frame. So, here I can write say in general, say I am interested in knowing these velocities with respect to frame B of the origin of frame B, and here you have say velocity frame A expressed in terms of frame A. So, these things are given, then using this equation I can write this matrix. How come this come? First one, you see we are talking about a structure over here. So, we do not have any joint velocity. So, this term becomes 0. So, here essentially we have the transformation. Okay. So, for angular velocity you just need to have a rotation matrix over here. So, contribution of this is going to be 0 and here you are going to have just a rotation matrix. Okay. So, this is done, and similarly for the velocity, here we are going to have this rotation matrix is going to be multiplied with this velocity as well as this one. So, for this velocity, so for this one we have this multiplication of rotation matrix, and this one has been written in this form. Okay, I am putting this minus sign here because here it is we need to change the order of the position vector and angular velocity vector, because I have got angular velocity over here. So, I have changed that order, and here I am talking about the P origin location with respect B origin location with respect to frame A. So, this way I can get this velocity transformation in the Cartesian space. Similarly, for the static forces I can use this force propagation equation, okay, for say I from I to I plus 1th frame, and similarly this moment propagation equation. So, again I can write it say my ith frame is say frame A and I plus 1th frame is my frame B, then I can write these equation in this form. So, here essentially we have got a frame transformation. Okay. So, for the force, so you have this rotation matrix, and here because of the moment we will be having this term also. So, it can be written in this form. Okay. Just check it wise we have done previously. So, to summarize, we have seen how velocity propagates, okay, angular velocity and linear velocity from one frame to another frame or one link to another link. We have evaluated the Jacobian, which is a matrix mapping which maps from the velocities, joint velocities to the Cartesian velocities. Okay, that is done, and the singularity limits our motion. So, every engineer, robotics engineer, has to keep this always in mind when they are designing that we may have situation where your joint may be rotating at infinite rate, but you will be losing, your manipulator may not be moving, tip may not be moving in a desired way. Okay, in certain direction it may be might have lost its degrees of freedom. So, that is going to be a limitation, and so these are the relationship of the Jacobian, which essentially relates velocity in the Cartesian space to the velocity in the joint space, and in this form, in the static force and torque, joint torque relationship, this comes in this form. Okay. So, with this, these are the references which you can refer further for your further study, and with this I would like to close for today's. Thank you.